All right, here we are into Chapter 5 now, the meat of chemistry, compounds and their bonds. So we've dealt with a lot of different topics so far. Now we're ready to dive into those electrons and what those electrons are doing and how those electrons are holding these compounds together. In this particular section, we're going to be looking at ions, which involves the transfer of electrons. So one species is going to have now more electrons than protons and therefore a net negative charge, and the other species will have less electrons than protons and will therefore have a net positive charge. And we'll look and see how that transfer of electrons causes a pretty strong, pretty stable ionic bond. Okay, so looking at ionic bonds, before we dive into that particular topic, let's compare and contrast ionic and covalent bonds. So atoms form octets. The idea of getting a valence electron count of 8 is a very stable state. We probably recognize that in the periodic table when we talked about periodic trends. We noticed that the atom size was the smallest and the ionization energy was the greatest for those group 8A or group 18 elements, the noble gases, so to speak. They're noble, which means inert, because they have a stable octet. They have the ns2-np6 configuration, and they're very nice and stable. It takes a lot of energy to ionize them, to remove an electron, because it's a stable state. Of course, helium at the far top right of the table has just the 2 electrons, the 1s2, but everybody else has an ns2-np6 in the noble gases, and they do very little chemistry as a result. They're nice and stable. So the other atoms are jealous, and they try to emulate that stable noble gas configuration either by losing, gaining, or sharing valence electrons. So by losing and gaining, one species loses and one species gains. We see that process on the left of that picture where the metal gives up its electron to the nonmetal, and then we end up with an ionic bond, a metal cation and a nonmetal anion. And notice the metal cation is smaller than its parent metal, because now its valence electrons are being held more tightly. It's got a positive charge in the nucleus, so fewer electrons, same positive charge, it gets smaller. Notice for the anion, the negatively charged species, we got larger in the ion compared to the neutral atom, and that's because now we still have that same positive charge in the nucleus, but we have an additional electron to deal with, and that causes sort of a puffing out of the anion compared to the neutral atom. That's the transfer. That's the gaining and losing part. If we look at the right-hand side, that's the sharing part. So the 2 nonmetals, this would be like fluorine and fluorine, for instance, where each has 7 valence electrons. If they can share that one unpaired electron with each other, now, as long as you look at it sort of like a Venn diagram where there's that overlap in the middle, so you can think of them as each having 8, although neither one fully owns that pair that's shared in between. But it's still a more stable situation than having the free atom with just its single unpaired electron there with 7 valence. And that's why we will talk about the diatomic elements, things like fluorine, chlorine, and bromine, and iodine, those group 7 elements that do pair up in nature because it's much more stable for them to be sharing that pair of electrons in a covalent bond than being free atoms like the noble gases would occur. So following up with that idea of covalency, sharing, being together, so having their valence together, covalent compounds are formed when 2 nonmetals, either the same nonmetal with itself or 2 different nonmetallic elements, share valence electrons to form that covalent bond. And so covalent compounds are molecules. They're discrete, and they're not, as we'll come to see with the ionic and metallic bonds. We'll just touch on metallic bonds briefly, but those are very long-term interactions. These covalent compounds are discrete, small things like water, carbon dioxide, glucose, and even really large things like proteins in our body. They're largely consisting of these covalent bonds. So they're sharing, they're fairly strong when there's a lot of them. Water is quite a stable molecule, for instance. But again, as we'll see, ionic bonds tend to be stronger than covalent bonds, at least with respect to the macro scale, where we see things like water having a lower boiling point and melting point than things like sodium chloride. That has to do with the type of interactions you're actually overcoming. Alright, so looking at ionic compounds now, they're formed when metal atoms transfer their electrons to nonmetal atoms, which result in those ionic bonds. So we have a full transfer of electrons. So some common ionic compounds, table salt, that's, if you think of it, a sodium atom and a chlorine atom came together, and that sodium atom gave up its one valence electron to the chlorine, which was lacking just one from having an octet. And now you have an Na plus and a Cl minus, and they're both very happy and much more friendly to us as human beings than if you had sodium metal and chlorine gas. Each of those substances is quite toxic. Sodium chloride, it's not great for you in large amounts, but we do need a little bit of it every day. Baking soda, another example of an ionic compound, sodium hydrogen carbonate, and then milk of magnesia, magnesium hydroxide. Continuing with that theme of ions and transfer of electrons, if we think about the minerals, a lot of common minerals, including our precious and semi-precious gemstones, consist largely of ionic bonding. So sapphires and rubies are made of aluminum oxide, Al2O3. That's a metal and a nonmetal, right? Aluminum's a metal, oxygen's a nonmetal. So they form an ionic compound, and they give beautiful colors, depending on whether we're talking about ruby, which is a particular amount of chromium impurity to give it the red color, or the rest of the substances known simply as sapphire. It's iron and titanium which make them blue, although you can have other impurities to make them other colors, even colorless. So if they're any color but red, including colorless, we call them sapphire. If they're red in a certain range, it's because of the chromium, and then we call them ruby. But they're all examples of aluminum oxide, an ionic substance that's very high melting and very strong ionic bonding. So let's go back to that octet rule, right? It's the tendency for atoms to share or transfer electrons to obtain a stable configuration of 8 valence electrons. So we talked a little bit about the sharing of electrons, and that's our covalent bonding, and we'll go back to that a little later in the chapter, but for now we're focusing more on that transfer of electrons, and we see that, again, it tends to be a metal that loses, a nonmetal that gains, and each ends up with a valence count of 8. The metal, we don't commonly show it, but now its valence is like the previous noble gas, and then the nonmetal, obviously, we see that extra electron, and it's not always just one electron. We could transfer 2 or 3 or even sometimes 4 electrons for these ionic substances, but there is a full transfer of electron, gives up ownership, as opposed to that sharing that we see in the covalent case. And so just a reminder about that octet rule, what we're trying to fill or to lose until we have is the noble gas configuration. So helium is just a duet. It has just the 1s2 orbital filled, and it does very little chemistry, so we don't worry about it anyways. But the remainder of that, group 8, we have neon having the 2s2 2p6, argon 3s2 3p6, krypton 4s2 4p6. We don't consider those d electrons really valence because they're from the previous level of principal energy level 3 instead of 4. So that's why we skip over those, although they can be important for the transition elements. For the main group, we tend not to do so much with the d electrons. The theme is ns2 np6, right? Whether that's period 2, 3, or 4, we see they all end in the ns2 NP6 arrangement for their valence, and that's what the metal is trying to lose enough to get back to the noble gas that precedes it. The nonmetal typically gains enough electrons to reach the same valence electron count as the noble gas that follows it. So that's why we tend to get positive for the cations and negative for the anions, and the numbers tend to match up with the group. So group 1 metals have just 1 electron in their ns orbital, so they try to lose that to become a positive 1 and then have the noble gas configuration of the preceding noble gas. The nonmetals tend to gain. If we're talking about group 6A or 16, they're trying to gain 2, so we get things like oxygen 2 minus that needs those 2 electrons to get the 2s2 2p6 configuration of neon. Okay, so focusing on those metals first, the metals lose their electrons to become positive ions known as cations. So it's caused by the loss of the valence electrons, and they tend to stop losing electrons when they achieve the electron configuration of the nearest noble gas. And for that reason, they have fewer electrons than protons. They have a net positive charge, and depending on where in the table we're looking, we tend to see that the group 1A or group 1 metals tend to lose 1 electron to become a +1 ion. Group 2A or group 2 metals tend to lose 2 electrons to become a +2 ion. Group 3A or group 13 metals tend to lose 3 electrons to become a +3 ion, and that's just the necessary number of electrons to get to the noble gas that precedes it. Okay, so we have this nice picture here showing us the formation of a sodium ion. So going from neutral sodium atom, Na neutral, to the sodium ion, Na+. And it achieves that octet, the neon electron configuration of 1s2, 2s2, 2p6, by losing that 3s1 electron. So notice nothing's happening with the nucleus. That was the previous chapter where we talked about the nucleus. Now we're keeping the nucleus fixed at 11 protons. That's why we're at the element sodium, because the sodium is the element with 11 protons in its nucleus. We start as the neutral sodium atom, which has also 11 electrons to cancel out those 11 positive charges from the protons. As we lose that valence electron, we're down to 10 electrons total, the same as neon, and now we have a net positive charge. We have 11 plus charges in the nucleus, 10 negative charges outside, so we have a net +1 charge, and we see the electron cloud gets noticeably smaller as we lose that electron, and now have the 11 positive charges in the nucleus, really only holding 10 electrons in the valence. Okay, so we already talked through it, but those who benefit from seeing it, there we have it. The sodium atom versus the sodium ion. 11 protons, 11 electrons, 0 for the overall charge. Sodium ion now, we have lost that 1 electron to give still 11 protons, 10 electrons, and a net positive charge, +1. Or 1+, you see it both ways, and we tend to accept it either way. If we move to the next column, we have now magnesium becoming the magnesium ion. So in order to achieve an octet, magnesium now has 2 valence electrons, right? It's 1s2, 2s2, 2p6, 3s2. We need to lose both of those 3s electrons in order to form the magnesium ion, the stable neon-like configuration of 1s2, 2s2, 2p6. So as we see here, we start with the neutral magnesium atom, which has the 2 dots in its electron dot symbol, and we lose both dots to become the magnesium ion Mg2+, and we see that now we're even smaller because we have a positive charge of 12 due to the 12 protons in the nucleus. We were countering that in the neutral magnesium atom with 12 electrons. Once we lose those 2 electrons, now we've got 12 protons, so that nucleus has net charge of 12+. The electrons, there's only 10 minus charges outside, so the nucleus is going to hold those 10 electrons even closer in the case of the magnesium 2+ ion than the sodium 1+ ion did with its 10 electrons and 11 protons. And as you see with the electron configuration, we've gone down from the 1s2, 2s2, 2p6, 3s2 of the magnesium atom to now 1s2, 2s2, 2p6. Just like neon, we have that filled second principal energy level, 2s2, 2p6, and that's why we form a +2 ion to get to the stable state for the magnesium ion. Again, a nice visual showing of the math, if that's helpful to you. We have the 12 protons, 12 positive charges in the magnesium atom, balanced by 12 electrons in that neutral magnesium to give 0 charge. When we lose those 2 3s electrons, we now have 12 protons still. We're still the element magnesium, but now we have just the 10 electrons, the 2s2, 2p6 valence to get the octet, and that gives a net positive charge of 2+ or +2. The convention is to show 2+, but again, if you look at some older texts, you might see +2, and I tend to accept it at this level. If you go on in chemistry, your next instructor might have a little more of an issue with that than I do. All right, let's pause now for a learning check. Let's see how this idea of transferring electrons is going here. So the first question, what is the number of valence electrons in aluminum? That's just the neutral aluminum atom. Number 2, what does aluminum require to acquire an octet of electrons? Number 3, what is the charge of an aluminum ion? And number 4, what is the symbol for an aluminum ion? So go ahead, pause the video now, make your selections, and we'll start back up and see how you did when you're ready. Okay, number 1, the valence electrons in neutral aluminum is 3, right? It's in column 3A or group 3A or group 13, however you prefer it. And that's because it is a 1s2, 2s2, 2p6, 3s2, 3p1, right? In that valence, the principal energy level 3 for aluminum, we have a total of 3 electrons, the 3s2 and the 3p1. Number 2, what does aluminum require to acquire an octet of electrons? Well, it needs to lose those 3 electrons. It's a metal. It's easier to lose 3 than to gain 5 to get to an octet, right? So metals tend to lose because they tend to have less than 5, or less than 4, really, for most metals. Although when we get down to tin and lead, we'll see that we can lose 4. But we tend to have 4 or less electrons, we'll say, and so it's easier to lose them than to gain. Number 3, what is the charge of an aluminum ion? Well, therefore, if it's going to lose 3 electrons, it's going to maintain that same nuclear charge of 13 protons, so 13 plus, and then to lose those 3 electrons, it's going to have now just 10 electrons in its valence, and that's going to give a net charge of 3 plus. And finally, what is the symbol for an aluminum ion? It's aluminum 3 plus, right? The 3 plus as a superscript following the aluminum's chemical symbol of capital A, lowercase l. Hopefully that went well. We'll have another learning check later on in this lecture, but if you're having trouble with that, please do try some problems. Get the hang of it. It's just takes a little getting used to, but once you're there, it's not a very hard concept. It just takes a little practice sometimes. Okay, so that was how we form these positive ions, these cations for metals. Now let's take a look at the process for ionic compounds from the nonmetals forming the anions, the negative charge, right? So they do so because the nonmetals are to the right of the periodic table, generally in group 4 and beyond, so it's easier to gain the 4 or 3 or 2 or 1 electron than to lose 4 or 5 or 6 or 7 electrons. So that's why they do that, to achieve the octet arrangement, and they've therefore formed negatively charged ions called anions, most commonly with 3 minus, 2 minus, or 1 minus charges, right? Group 4 or 14, 4A as it's known, you tend to see a lot of sharing there, especially with carbon. Actually, the whole course 142 is devoted principally to the chemistry of carbon. So it's special because it's in group 4 and because it's small. It tends to do a lot of the covalent bonding, the sharing that we mentioned early on in this lecture, rather than gaining or losing, because it's right in the middle of the road. It's at 4, it's halfway to 8. Does it lose 4? Does it gain 4? Typically it does neither. It does much more sharing. So we tend mainly to talk about metals having charges of 3 plus, 2 plus, or 1 plus, and then the nonmetals having charges of 3 minus, 2 minus, or 1 minus when we're dealing with ionics, full transfer of electrons. When we're dealing with nonmetal and nonmetal, we tend to be looking at sharing, and carbon does it like no other element in the table. Okay, so back to that idea of making these anions, we have the formation of a chloride ion, a Cl- from a neutral Cl atom. So chlorine's in group 7A or group 17, so it's just 1 short. It has 7 valence electrons. It's just looking for 1 more, which explains why it's so reactive. Generally, when you're missing just 1 as a nonmetal to get that 8 octet, or you have just 1 extra like the group 1 or group 1A alkali metals, they tend to be very reactive because they're really after that 1 electron, either to gain it in the case of the halogens, the group 7A elements, or to lose it in the case of the group 1A metals, the alkali metals. So we see here the neutral chlorine atom with its 7 electron dots. It's got 17 protons and 17 electrons in its neutral state, and therefore its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. When it gains that one valence electron, it becomes now the chloride ion. Notice we have 8 dots around us now and a negative charge. That's because we have still just the 17 protons in the nucleus that make us chlorine, but now we have an extra electron in the outside, which makes us chloride as opposed to neutral chlorine. And therefore our electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, is now a stable noble gas configuration with a total of 8 valence electrons, 3s2, 3p6. Here again, to show it visually for those of you who like your math in a more traditional format, we have the chlorine atom, 17 protons, 17 electrons, net 0 charge. The chloride ion, 17 protons still, but now 18 electrons to give that 1 minus net charge on chloride. Okay, so finding those, or at least predicting the most stable ionic charge from the group number, it tends to be a little easier with the metals. So positive ions will have a charge that equal their group number as long as you use the A nomenclature. So group 1A or group 1, either way you're going to get a +1 there, or 1 plus I should say. Group 2A or group 2, you're going to get a 2 plus, and then group 3A or group 13 is where it starts to get tricky there, because we've gone past the transition metals now to get to things like aluminum or boron. We tend to expect a 3 plus charge. If we're dealing with the negative ions, things get a little trickier, because even if you're using the A nomenclature, you've still got a slightly more difficult math problem ahead of you. The anions, the negative ions, tend to form from their group by losing enough electrons to get to a total of 8. So if we take the group number, if we're dealing with the A's, we'd say group 6A would be 6 valence electrons minus 8 gives us a -2, or 2 minus charge, as our convention is. If you're going to stick with the higher numbering system without the letter beyond it, this would be for the same elements. Things like oxygen and sulfur would be now in group 16, so we would do 16 minus 18, so we'd still get that 2 minus. You just have to be consistent whether you're using the 6A nomenclature, for instance, or the group 16. That's going to change your group 8A or 18. As long as you're consistent there, you'll end up with the right value. But if you mix them up, you'll end up with either far too many or far too few electrons. So be careful. Pick a way now and stick with it. Both ways are right, but if you mix them up, you can easily end up with something incorrect. Okay, so here looking at table 5.1, we see some symbols and names of some common ions, and they follow those rules pretty nicely, especially the metals. The main group metals are your best friend in the course. They very rarely steer you wrong. So if we look, group 1A or group 1, we have lithium plus, sodium plus, potassium plus. Notice the name of the cation's the same as the name of the metal, we just understand it to be an ion. So if we want to be really careful, we would say lithium ion and sodium ion and potassium ion, but we're not usually that careful. If we look at group 2A or group 2, we have Mg2+, Ca2+, Ba2+. They're all now 2+ ions because they have the 2 electrons to lose in that ns2 orbital, or ns orbital filled now because they're in group 2 or group 2A. And again, we just name them like we would name the metal. Be careful because calcium, for instance, there used to be a toothpaste commercial where they would advertise liquid calcium. Well, they should have probably said aqueous calcium ion, because to really get liquid calcium metal would be a very high temperature, and you probably wouldn't want to put toothpaste at that temperature into your mouth. So just be careful. Chemists themselves often get lazy with this, but be careful always to try to say ion if you're talking about the metal ion versus the neutral metal. If we look to the right side, now we have the common nonmetal ions. These tend to be just one of a variety of possibilities. So just be careful. If we're dealing with the true metal ion, we would expect group 5A or group 15 to give us 3- ions, and we'd expect things like N3-, P3-, nitride, phosphide. Those are true and correct. For 6A or 16, we'd expect oxide to be 2 minus and sulfide to be 2 minus, because again, it's either 6 minus 8 or 16 minus 18. Either way, we would get to that 2 minus. And then finally, group 7A or group 17, F minus, Cl minus, Br minus, I minus. Notice we went down even further because group 7A or 17 tends to be a little more predictable in their behavior. We didn't go down very far in the others because we start to get into that metalloid territory where things get tricky, but these metal or non-metal ions tend to be pretty predictable, tend to be pretty safe. These are the ones you should really know and expect to see a lot of here. And obviously for the non-metals, the name has changed. You take the root of the non-metal element and change the ending to IDE. So we get nitride, phosphide, and oxide as opposed to nitrogen, and phosphorus, and oxygen. So we don't have the same problem where people might mistake the ion for the metal. That tends not to happen if people are rigorous about their non-metal ionic naming. Okay, and there we have it, nice and visually organized here. Lithium, when it loses its 1 electron, it therefore ends up being just a 1s2, so it has the noble gas configuration of helium. Beryllium we don't talk about. It tends to do a lot more covalent type bonding. It could be coerced into being a Be2+, but that's unusual, so that's why that's missing from our table. And then everybody else we see looks like it has a noble gas configuration of neon or argon or krypton or xenon, something larger that would have a true octet. Lithium ends up with just a duet after it loses its 1 electron. But everybody else on our table here ends up with a true octet, and depending on where they were, if they were in group 1A or 2A or 3A, they form +1 or 1 plus, 2 plus, 3 plus respectively. If they're in group 5A, 6A, 7A, then they form 3 minus, 2 minus, or 1 minus, respectively, in order to achieve the next noble gas, whereas the metals are trying to achieve a situation like the previous noble gas. So metals will lose until they get to their nearest noble gas, which will always result in a positive charge because they're going back in the table. Non-metals will always gain electrons to go forward in the table to the nearest noble gas, and to get those actual numbers, you take the group number, and if you're dealing with the metals in the A nomenclature, you just turn that group number into a 1 plus or 2 plus or 3 plus. For the non-metals, you'll take that group number. If you're using the A's, you'll subtract 8 from it. If you're using the higher numbering scheme, then you'll subtract 18 from it. But either way, you should arrive at those 3 minus, 2 minus, or 1 minus values for groups 5A, 6A, and 7A. All right, so hopefully you've been able to follow along with us. I've tried to keep it simple and use very familiar, very typical cases. Things with ionic bonding get very convoluted in those transition elements. They tend to be able to lose from their S and their D sublevel, which makes them really tricky. So the main group is where we focus. The main group is largely what you're responsible for, and hopefully that nice predictable main group is going well. If not, we're going to do a learning check here to see, but if things aren't going well, please don't hesitate to get in touch with me to find some additional practice problems to just get used to this bonding scheme that we call ionic bonding. Okay, so as promised, here's a learning check where we're going to look at those nonmetals and see how we do. So number 1, what is the group number for sulfur? Number 2, what is the number of valence electrons in sulfur? Number 3, to acquire an octet, what does sulfur require? And number 4, what is the charge of sulfur ions? Go ahead, pause the video, make your selections. When we start back up, we'll see how you did. Okay, so hopefully in your periodic table you had little trouble finding sulfur, capital S there, in group 6A or group 16, depending on which of those you prefer. The 6A stuff is easier for here and now, but the 16 is more and more common. Number 2, what is the number of valence electrons in sulfur? Well, it has 6 valence electrons. Number 3, to acquire an octet, what does sulfur require? Well, rather than losing those 6, it's far easier to gain 2 electrons. And now number 4, what is the charge of sulfur ions? Well, if they're going to gain 2 electrons without changing their number of protons, they're going to acquire a net charge of 2 minus. Hopefully this was relatively straightforward. It is a little trickier to do the nonmetals versus the metals when we deal with ionic bonding, but hopefully by now you're comfortable with either, and if that's not the case, you're pushing yourself to do more practice problems and certainly to reach out to me for additional help if needed. Alright, so we'll pick back up with the next section of Chapter 5.